Надаю тепер слово панові Москаленко з Фізично-технічного інституту високих температур Харкова.
Nanocrystalline titanium. Мова буде йти про формування nanocrystalline.
So we'll be talking about bulk nanocrystalline titanium, where grain is less than 100 nanometers, which is created by cryomechanic fragmentation of the grain of a metal of industrial scale. Creating of nanocrystalline titanium is an alternative to
Відомо, що саме як функціональні, так і конструкційні властивості
to alloy addition. The properties of materials largely depend on the structure, and the lack of the lower hardness is the main hurdle that doesn't allow to use alloys for non-alloys in various fields, in aerospace technologies and medical implants. The existing methods of obtaining nanocrystalline materials with using the plastic deformations have a number of disadvantages. And I will later list the advantages of this particular method, but what I want to say is that the technology itself and its basis is based on the results of the fundamental studies of mechanisms of plastic deformation of titanium and titanium alloys, which have been done for over many years now in Physical Chemical Institute of Low Temperatures, named after Verkin at the National Academy of Sciences. Down to 0.5 kelvins. The characteristics of titanium that are formed in the nanocrystallic state. The best thing here is that creating the nanocrystalline state in a titanium of the highest purity. Nowadays there is no such a method that could be applied for this type of refinement of titanium or zirconium, and 30 nanometers is the thickness which cannot be achieved still in the best labs over the world. But another thing, the flow threshold of titanium is increased 8-fold when the grain is reduced to 40 nanometers. 120 megapascals to 1030 megapascals. And with a ductility 22%. For technically pure titanium, this is only the strengthening process is additive. Is comprised of the additives that are present in the metal of the previous content. What is it, nanoscale grain? To the right. The nanometers. Oh no, excuse me. This is a clear mistake here. No, yeah, my mistake. So 35 to 40 nanometers for technical titanium compared to other titanium, aluminium, 6 vanadium. The physical basis of these technologies and development. Titanium is twinning with the lower temperatures. And at the bottom we have optical structures for titanium. And the initial size of the grain, 15 micron. And every grain is fragmented by twinning. This is the very mechanism. With the increase of plastic deformation, cryo deformation, the size of the grain decreases significantly. And high purity titanium will have a size of grain of 30 nanometers. Technical titanium has a larger size of the grain. I'd like to say that the materials that were used in various spheres, especially for medical implants, they must have not only technical properties but functional. So the technical properties, for technical properties, maybe the 100 nanometers of grain size will suffice. But if we talk about physical chemical properties, corrosion resistance, biocompatibility, bioactivity, here the refining of the nanoparticles, further refining of the nanoparticles is very important for functional properties. But in order to break the threshold of plasticity, at the same time increasing the hardness, we suggest the bimodal structure, which will include the nanocrystalline matrix will have a share of submicron size grains. We don't have the patents, there's only declaration of patent. And these are the results and the participants in these studies. And these are some of the advantages: the hardness, the fatigue, strength, resistance to friction. Titanium has a very low friction resistance, and the previous studies shown they're still ongoing. With the refining of particles, the wear resistance also changes. Now, to conclude, the existing methods of alloy pressing will only produce smaller samples, smaller grain bigger grain sizes and smaller samples. Our technology allows to apply the existing methods of metal treatment. All kinds of metal treatment that are regularly applied, they can be applied for producing these technologies. The Russian Institute in Ufa is the only organization that could produce a rod 8-meter long and 2 millimeters in diameter. It's hard to say economically. Economically, we don't know yet. We only can presume that it is highly attractive. For investors, it is attractive because it is easily commercialized. For instance, the liquid helium as a cooling suspense is easy to obtain in oxygen producing factories. And just as nitrogen, the liquid nitrogen, which is used for cooling, there can be used for making materials. Okay, the words are written here, but they are a general. They offer a general overview. As for the thresholds and barriers that still have to be conquered, in order for this technology to be successful, we need the joint effort of medical workers and scientists. Only by joining our efforts we can optimize the properties of biomedical properties and material science.
Thank you very much.
Thank you, Dr. Moskalenko.
I have one question from internet.
I have obtained one question from the internet to Professor Moskalenko.
Yeah.
From Professor Leonid Dolgov from University of Tartu. So the question is about the comparison of boron nitride with similar analogies. Because Belarusian colleagues from the Institute of Super Hard Materials, they produce a similar type of materials. Could you please reply shortly to Mr. Dolgov? What are the characteristics? I don't think that we can compare the way our question states. They are different materials. Our material is based on the boron nitride. The Belarusian material is pure cubic boron nitride, which is sintered at the high pressure, 10 gigapascals. And a very important thing here is that the technology doesn't give an opportunity to obtain industrially applicable samples because they are only 3 to 4 millimeters maximum. We offer for the metallurgy where they need bigger parts, so it's a realistic tools. What they produce is just a material, it's just a sample, it's not a tool. We are talking about the tools and we offer them. Okay, are there any questions to Mr. Moskalenko as far as titanium alloys is concerned? what is known in the world, in the U.S. and America about these materials? Are they absolutely original? This is that's a question to Mr. Moskalenko. The studies are available in Russia by Professor Valiev. As I said, they obtain nanostructured titanium, which is titanium but submicron grain size, no less than 200 nanometers. It's not bad for increasing the physical properties, but as for smaller sizes of grain, in Australia they have the research in this regard, and in China. Liquid nitrogen and treatment at lower temperatures, maybe it's not too widely spread. Thank you, Dr. Moskalenko.